Okay, let's get started. Oh, that's loud. Okay. All right, let's get started. First, let me pull up the calendar here. I want to point out a couple things. Okay, so today is October 6th. We're going to go over lesson 19. We're going to cover two sections, rates of change in natural and social sciences and hyperbolic functions. Next Monday and Tuesday, notice we have fall break. So no class on Monday, no recitation on Tuesday. Okay. Also take a look at what we'll be doing in the few days after we come back. We'll be focusing on applications of the techniques we've been learning. Exponential growth on Wednesday, related rates on Friday, and the Monday after that. And also look ahead just a little bit more, October 19, that's exam 2. Okay. And I'll have more to say about exam 2 next week after we come back from the break. So once again, no class on Monday and no recitation on Tuesday. Notice that nothing is due on Tuesday either. So you do get a genuine break, at least for this class. All right, so the first section we'll cover today is section 3.7. There's nothing new as far as techniques is concerned. We're going to be applying what we have learned to simple things in some applications. And we're not going to go terribly in depth with these applications either. There's time for that when we deal with related rates and maximum and minimum later. So we're going to revisit a problem that we have solved before. And now we know how to deal with derivatives very quickly. We can dig a little bit deeper into this thing. Let's say we have an object and this thing is thrown upward such that its height measured from the ground is this function. H of t is equal to 144t minus 16t squared. Okay, we've seen something very similar to this when we first encountered derivative, when we talked about the average velocity, the instantaneous velocity, and then we looked briefly at acceleration a little bit after that. So let's just take a look at what's going on here. Of course, we know what's going to happen. From our physical intuition, if we graph the height versus time, at time 0, we're starting from the ground. And at some time later, it comes back to the ground, right? So we know that's the shape we're getting. And also from this t squared here, you know you're dealing with some kind of parabola that opens down because of the negative sign. Okay, do you remember how to find the time when the maximum height is reached? Velocity is 0, right? Yeah, that's right, the momentary stop here. So let's find the velocity. V of t, of course, is h prime of t. And that's very simple, 144 minus 32t. And we know that maximum height is attained at the moment when the velocity is momentarily 0, when it goes from upward to downward. That brief moment is when the maximum height is reached. So if you set this equal to 0, solving for t turns out to be 4.5. Okay? 4.5 seconds after we launch this thing, it reaches maximum height. Okay, do you remember how to find the time it takes for this thing to come back down? What's that? It's double that, but in general, how would you find that? When h is equal to 0, absolutely. So let's find this time too. Okay, and he's absolutely right. This is a parabola, so that the vertex is halfway between the two intercepts. But more generally, you would take the height equation. It's not always going to be a parabola in general, in most general applications. Here we got a parabola, great. But in general, you would just make the height equal to 0, and then solve for t, right? You can pull out a 16t from both of these and you get 0, that's when we start. And then 9, that's obviously when we come back down to the ground. Let's find the acceleration. Acceleration is the derivative of velocity. We'll call that a, v prime of t. Here's v. Derivative is negative 32. All right. Where's that acceleration coming from? Knowing the physics behind this problem, what's causing that acceleration? Gravity, right? Gravity is the reason why there's this constant acceleration. And what's that minus sign telling us? Down, right? Now we hope gravity is always going down. Okay, now all of this stuff we've done before, nothing super new here. Now let's take a look at what's happening here. Let's graph the velocity and the acceleration. I'll write down the velocity equation from the last page. 144 minus 32t and this is of course a straight line with a y-intercept at 144. And remember, it reaches 0 at 4.5 for t, and then 9 is when this entire thing stops being interesting, when it comes back to the ground. And you can plug in 9 into here to find out the velocity at t is equal to 9. That turns out to be minus 144. Coincidence. So this is the velocity right before the impact. Right, downward at 144, whatever unit we're dealing with for length and time. So we could say meters per second, for example, or feet per second. 32 would be measured in English units. Now let's graph the acceleration. The acceleration is a constant function we saw, negative 32. It's a constant function, so just a straight line, horizontal line. And I want to line up the t numbers too. So here we go. Okay, now let's see what's going on here. From the time we launched the thing, between 0 to 4.5, Positive velocity means the object is going upward, right? Negative acceleration means gravity is pulling it back down. During that time, from our intuition, we know the object is rising and slowing down, right? It's going up and slowing down. So let's write that down. Between 0 and 4.5, velocity is positive because it's rising, but acceleration is negative. Gravity is downward. And we know from the simple physics behind this that the object is slowing down. And that makes sense, because if you have a positive velocity and a negative acceleration, that means that the velocity has a negative rate of change. As time goes on, the negative rate of change is going to try to decrease the velocity. And eventually, they'll pull it back down, reaches 0, and then pull it back down. Object is slowing down. Now, on the second half of this motion, between 4.5 and 9, velocity is negative. Acceleration is also negative. We notice that the object is speeding up. Right? We all know what happens when you drop something from a height. It'll pick up speed, eventually reaching what's called the terminal velocity if air resistance is accounted for. We're not accounting for air resistance here, so we're not going to be able to see the terminal velocity from this simple model. But we know, at least before reaching that point, object is going to get faster and faster and faster. And this is a very easy way to tell what's going on in general. You look at the signs of the velocity and the acceleration. If their signs are opposite, that means they're fighting against each other. The object is going to slow down as time goes on. So let me summarize that thing there. If velocity and acceleration have opposite signs, the object will slow down. Okay? Think of remember, the sign in this kind of modeling tells us about the direction. If you're going one way and your acceleration is the other way, over time it's going to slow down, just like the object rising and falling problem here. If they're going in the same direction, then they're helping each other. The acceleration is helping the velocity. So the converse is if velocity and acceleration have the same sign, object will speed up. Okay? So if you can get the velocity and acceleration graph, even if you don't truly know what the motion of this object looks like, you can always tell just by looking at the signs what is happening. Speeding up, slowing down, that kind of thing. And once again, the reason behind this is you got to think in terms of directions. Same sign means the same direction. You're going this way and your acceleration is going forward, same thing with you, then you will speed up. If you are going forward and acceleration points backward, then you will slow down. Does that make sense? Yeah? Okay. All right, let's try this on this simple example here. Here I'm going to sketch the graph of the velocity of some moving object. And it's going to look suspiciously like a sine graph. And that's fine. Starts at t equal to 0. And let's say the motion stops being interesting at 4. And we'll divide the time into 4 equal increments. Okay, so something is moving around, and somehow I obtain the velocity of this object. Between 0 and 2, this thing is positive. Between 2 and 4, this thing is negative. Now, how it's moving and all that, we don't really need that information. We have the velocity. So I want to find out here. What I want to find out is on what intervals is the object speeding up or slowing down? All right, so here's my velocity thing here. Changing signs means changing directions. So it's going one way for half of the time, going the other way for half the time. There's some kind of switch at t is equal to 2. You can think of positive as going up, negative as going down. Okay, so how do we find out when this thing is speeding up or slowing down? Just like in the last example, we want to look for the signs of the velocity and the acceleration. Remember how to sketch the derivative of something? It was on exam 1, right? I have a graph of this function here. I want to know the derivative of that. Do you remember how to sketch that? What do we do first? Right, we can start by finding out when the tangent line is 0, horizontal. So that's a good helpful step. So if you don't remember how we did it, here's a nice little review. You start out by finding when the tangent line is horizontal. And we see that happens at t is equal to 1. And t is equal to 3. Okay, so it's going to be right here and right here. Then we start moving from those dots, start looking at what's going on between two of them. So in the middle portion right here. From 1 to 3, notice that the tangent line on this graph is always negative. Always negative. Starts at 0, ends at 0, but remaining negative the entire time. So we should expect something of that kind of shape. And then beyond 3, going to 4 and beyond, notice that the tangent line slope, we don't care where the graph really is. We care about the slope. This is always positive. Starts at 0, seems to be getting more and more positive, bigger and bigger positive number as time goes on. So we get this kind of thing going on here. To the left of 1, slope is always positive. So the derivative should be always positive. So something kind of like that. Okay, so we know how to do that from a while back, sketching the derivative of something given the graph of this function. And now we check the signs of both of them. And everything is lined up, so that's very easy to find. Let's look at this first interval right here. between t is equal to 0 and 1, velocity is positive, acceleration is positive. Same sign, right? So this thing will be speeding up during that part of the motion. Now look at the interval between 1 and 2. Velocity is still positive. Acceleration is negative here. Opposite signs, they're fighting against each other. So velocity will, the speed will go down, slow down, slow down. Between 2 and 3, same sign, negative, negative. So this thing is going to be speeding up. And finally, for this last portion right here, negative velocity, positive acceleration, oppositing sign, it's going to be slowing down. Okay, that makes sense, because if the sign of the velocity is switching, that means the object is changing direction at some point. And in order to change direction, if you start running that direction, you want to change direction, you're going to have to come to a stop. You're going to have to slow down for at least a period of time before you can come back the other way. That's essentially what this thing is doing. It's going to the right, come to a stop, coming back. So there's going to be an alternating speeding up, slowing down kind of thing in order to achieve this kind of motion. Here, notice the acceleration is changing sign. So we got something in addition to gravity here. It could be a propulsive force of some sort. It could be a propeller, a rocket, who knows. Something else is changing the sign of the acceleration. All right, any question on this example? Okay. Does it make sense how you can use the velocity and acceleration signs to tell what's going on? Yep. All right, good. Let's do another example involving the change of something. Got a cube that's made out of metal. Each edge is X centimeters. And this metal tube is expanding because it's being heated. We know metal expands when heated, metal contracts when cooled. Each edge of this cube is lengthening at a constant rate of 0.1 centimeters per second. What we'd like to find here is how fast is the surface area of that cube increasing at the instant when x is equal to 2 centimeters. Okay, so this is venturing into a topic called related rates, which we will spend a great deal of time later on. But here's a very, very, very simple introduction to that kind of that topic, related rates. It's just dealing with something that's changing all the time. That's all there is to it. We know something's changing. We like to know something that's related to that, how this other thing is changing. Okay, so recap this problem here. We got a metal cube. Let's sketch it. Cube has the same side all around, right? It's made out of some kind of metal. And each side of this is a changing quantity, x. And x is changing because we're heating this cube. And this thing's retaining the shape, but lengthening. Each side is lengthening. The volume is getting greater. And also the surface area has to also get bigger as time goes on. Let's find out the surface area first. This cube has 1, 2, 3, 4, 5, 6 faces. 4 around and then top and the bottom. And each face has area that's x times x, whatever x is equal to. So let's call the surface area S as a function of x. 6 sides all around, right? 6. Each one having an area of x squared. So that's how we calculate the surface area of that cube. If I know x, I can tell you the surface area. But if x is changing, then the surface area has no choice but to also change. The problem asks us to find the rate of change. How fast is the surface area changing? The rate of change of the surface area with respect to time, right? As time goes on, at one particular instant, how fast is that surface area changing? It's like finding the velocity of that falling object at the moment right before the impact. At that particular instant, what is that object is doing? What kind of velocity does it carry? Same kind of thing here. At that one moment in time, if you could freeze time, how fast is that surface area changing? We want to find this quantity at a particular instant when x is equal to 2. Okay, so that's what's going on here. We're dealing with this. We know x is changing. We want to know that at particular time when this is happening. Let's see what's going on here. Because x is changing with time, and S, the surface area, depends on x. That means this surface area is really a function of time, right? So S depends on x. The surface area depends on the length of each side. That in turn depends on time. We got two things. We got changing in time triggering a change in x, which in turn triggers a change in the surface area. It sounds like a chain rule kind of thing. Yeah? You got something changing, the chain reaction happens, and then propagates down. It's precisely a chain rule kind of situation going on. So if we want to find the velocity, the rate of change of the surface area with respect to time, by the chain rule, we know we have to find how the surface area is changing with respect to what it depends on, ds. Dx, sorry. Right? S depends on x. So how is that happening? And then we chain together how that quantity x is changing with time. Okay, the variables change here, but this is just the classical chain rule that we've been dealing with. dy dx is dy du, du dx. ds dx, we look at this equation here, that's simply 12x. What about dx dt? What do we know about it? Why is that? Yeah, we're told, right? dx dt is the rate of change of x with respect to time. And we're told that each edge is lengthening. That means it's a positive rate at the rate of 0.1. Very simple. Okay, so what do we get? We get 1.2 times x. So this is saying that how fast the surface area is changing depends on what the length is. The bigger it is, the faster it is changing. The smaller that is, the slower it is changing. If you imagine a very big cube here, even a very tiny change in x is going to result in a much bigger surface area. So the x remains to be found. Well, we need to know what x is. And now is where this part comes in. This obviously depends on x. So at the particular moment when x is equal to 2, one particular moment we know x is equal to 2, the rate of change of the surface area with respect to time is 1.2 times 2. That's 2.4. And the units will be centimeters squared per second. So that's the thing we're looking for. This is how fast at that particular time the surface area is increasing. At that moment in time, when x is precisely equal to 2, that moment in time, the surface area is getting bigger at the rate of 2.4 centimeters squared per second. Roughly, if you wait another second, the surface area will be 2.4 bigger than the previous second. Questions on this example? Okay. Notice that this really is just a chain rule, right? We know the chain rule. We're just simply applying the chain rule that we know in a situation that is precisely what the chain rule deals with. We got three things happening. Time is triggering a change in this, which in turn triggers a change in that. That's exactly what chain rule can do for us. So all we did is tweaking the chain rule, changing variables, and then to come up with this number here. Like I said, this is getting into related rates, and we'll do a ton more of those things later down the road. But this is a very nice little simple introduction to that. No question on this one? Make sense to everybody? Yeah? Okay. All right. For the second half, we're going to look at part of section 3.11. We'll look at these things called hyperbolic functions. They show up in many physics and engineering applications. But they really are just exponential functions. Certain combinations of e to the x and e to the minus x have special names. One of them is called a hyperbolic sine function. And this thing is written as, it's like a regular sine, but with the letter h attached to it, hyperbolic sine of x. It's defined as e to the x minus e to the minus x over 2. Okay, so that thing is called a hyperbolic sine function, abbreviated sine with an h, e to the x minus e to the minus x over 2. The hyperbolic cosine function is defined similarly, and it's also written similarly. You get cosine, the regular cosine with a hyperbolic h at the end of it. And instead of a negative, if you put a positive here, you get your hyperbolic cosine. And there's such thing as hyperbolic tangent, hyperbolic secant, hyperbolic cosecant, all of that stuff. And the relationships are the same as you're used to. So for example, the hyperbolic tangent is tangent with an h at the end. It's defined as the hyperbolic sine over the hyperbolic cosine, or e to the x minus e to the minus x over e to the positive x plus e to the minus x. This over that. Same thing with hyperbolic secant and all that stuff. If you know the first two, you know all the rest of them. And the reason why these things have special names like sine and cosine is because they behave like sine and cosine sometimes. Sometimes they behave like the regular. By the way, the regular things you're used to, those are called circular sine and cosine. For example, if you plug in 0 for x, we know regular circular sine of 0 is 0. And notice that the hyperbolic sine of 0 is e to the 0 plus e to the negative 0, which is minus. E to the negative 0 is still 0 over 2. And that's 1 minus 1 over 2, and that's a 0. So in that respect, it behaves like the circular sine. Same thing with the hyperbolic cosine. Circular cosine of 0 is 1. And you can see the hyperbolic cosine of 0 is e to the 0 plus e to the 0 over 2. That's 1 plus 1 over 2. And that's a 1. Right? So they behave like their circular counterparts in some respects, but not all. The first major difference shows up in their derivatives, and we'll take a look at that. And these are not trig functions. They look like, they behave kind of like trig functions in some way, but they're not trig functions. There's no trig whatsoever in here. So the things like many trig identities may not hold. There are lots of them that will change. Some of them stay the same. We don't need to worry too much about the new identities. Let's look at their derivatives. Let's take the derivative of the hyperbolic sine and see what we get. The derivative of hyperbolic sine, by definition, is the derivative of e to the minus x, e to the positive x, minus e to the minus x over 2. Which is the same as 1/2 times the derivative of e to the minus x, e to the positive x, minus e to the minus x. Continuing with this, derivative of e to the x is e to the x, minus derivative of e to the minus x is e to the minus x times minus 1. Remember the chain rule. The power is no longer just an x, so we have to account for that by multiplying by the derivative of that power, hence the minus 1. So at the end of the day, this is 1/2 e to the x plus e to the minus x, which, if you look back to the last page, by definition, this is the hyperbolic cosine. Okay, so this part behaves like the regular, the circular one. Just like the derivative of the regular sine is regular cosine. But the derivative of the hyperbolic cosine let's see what it is. Derivative of hyperbolic cosine by definition is e to the x plus e to the minus x over 2. Using the same steps, that 1/2 doesn't matter. Derivative of e to the x is e to the x. Derivative of e to the minus x is e to the minus x times minus 1. Once again, the chain rule applies here. Power is no longer just a plain x. Any modification to x, use the chain rule. Any modification. Chain rule supplies the minus 1, so this makes this a 1/2 times e to the positive x minus e to the minus x, which by definition is the hyperbolic sine function. All right, so there's the first major difference. There's no sign change here. We know the derivative of the regular cosine is negative sine. But in the hyperbolic counterpart, there's no sign change. The derivative of hyperbolic sine and cosine is always just the other one, never a change in sign. So they behave very much like the circular cosine and sine, but in this one important respect, there is a change. The regular trig functions always have a sign change with the co-functions, not happening here. All right, so what are these things used for? These things are related to a shape called the catenary. Catenary is kind of a parabolic-like thing, but it's not exactly a parabola. It's the shape of a hanging chain or cable or any kind of string under its own weight. If you go out and look at the power lines, for example, the shape that they have under its own weight with support on either end, That shape is called a catenary. It looks like a parabola, but it's not a parabola. And it turns out that the shape, the catenary shape, can be described very, very elegantly by using the hyperbolic sine and cosine. If you just use the plain old x, it gets complicated. But using those functions, it turns out to be a very simple shape. Catenary is used in a lot of architecture. For example, in the St. Louis Gateway Arch. Right, the thing is an upside down, kind of parabolic shape. From far away, you look at it, you say that's parabola. It turns out that it's not. It's actually a catenary. Okay? It's an upside down. If you imagine a chain that's very heavy, is hanging under its own weight, and turn it upside down, that's essentially what kind of shape you've got in that archway. The equation for that archway, which, if you're interested, is this thing. 211.49 minus 20.96 hyperbolic cosine of 0.0329175 times x. And x is measured from the, if I remember, from the center, I believe. And obviously the units here would be probably, I'm guessing, yards or feet to get the St. Louis Gateway Arch. Okay? And it's used in a lot of different other applications. The prominent ones are the ones that we can actually see, and you can see them in the architecture. Also, these are called hyperbolic because they're related to a point on a hyperbola. Related to hyperbola, x squared minus y squared is equal to 1. Remember, hyperbola is kind of like two parabolas opening the opposite directions. So if you graph x squared minus y squared equal to 1, you get these two branches. If you pick a point down here, that point is at the coordinate hyperbolic cosine of a, comma, hyperbolic sine of a, where this a is related to the area of this almost a triangle shape, but not quite. Okay, so it can be related to the hyperbola in some way. Pick a random point on there, name that point hyperbolic cosine a, hyperbolic sine of a, and that a will be half. The area of this little region right here will be half of a. So it is related to a hyperbola in some way. Not terribly useful in most applications, but that's one property it has. All right, that's it for today. Have a good fall break. See you again Wednesday. All right?